So hello everyone. Welcome to the session. Today's session we'll be talking about a next generation scheduling for both the YARN and Kubernetes, and it's pretty much focusing on the on-prem cloud hybrid environment, and basically to run a different type of workloads like services or batch workloads. So let us introduce ourselves. So myself Sunil. So I'm from Cloudera, and I'm an Apache Hadoop PMC and committer. This way. Yeah.
My name is Wei. I'm also from Cloudera and a Hadoop PMC member and committer, and working on YARN for many years.
Cool. So here is the agenda for today. So we will start with a journey through the big data experience, and just want to give a perspective in scheduling, like where we are today for both YARN and Kubernetes, and the real motivation why we need to improve the scheduling. And we'll be introducing something called as YuniKorn. I'll give more details inside and a short demo there, and I'll give you some of our standpoints in terms of how it's going to get shaped in the future. So yeah, let's start. So let's look at the customer journey in terms of the big data ecosystem as of today. So definitely there is storage, and we have Hadoop HDFS, which is a legacy, and that's where most of the data is stored as of today. And we have also the public cloud vendors. They have the storage, and most of the data is actually in either of these kind of file systems. And when you're looking at the compute perspective, there's like on-prem and on-cloud, we have the compute that is like a distributed or decoupled storage or compute kind of scenarios that we are going in. And predominantly YARN is actually there, which is basically scheduling all these batch workloads and services and so on in terms of the big data optimized way. And what it tried to do so in the first level is batch workloads, which is your MR jobs or your Thais or your Spark, or it could be your Hive queries, right? And which may be running with your Thais or MR inside. So this is where the batch workloads are running on top of YARN. And the way it progressed, like we also wanted to run some long-running service like LLAP for faster query process, and these are like called as, we say, a long-running service. It will be running for a longer time compared to normal batch workloads, and it will be staying there for a long time, and it actually will give you much better computation faster. And definitely streaming is one of the scenarios, and also LLAP like a scenario, or Impala. Like all these scenarios are actually focusing on this long-running service model. And with the addition of machine learning and deep learning, so we also had to support TensorFlow or MXNet running on the same cluster for better efficiency and for better resource planning and etc. And it has to run on top of Docker as well, because that was a de facto standard now, right? Because you need to be containerized and you need to be getting better resource isolation and etc. So Docker was actually there. And this was actually Kubernetes, right? So Kubernetes actually is optimized to run your containerized microservices very optimal way. So if I'm looking into, this is the arena in terms of today, how the customers and users are actually using their big data workloads. Now, there are a few more new trends actually, because in today's world, like we need to run even the big data on top of containerized way. There could be many reasons, like you need portability for the apps. You also need to have better resource isolation in terms of your GPU resources, and some dependency management in terms of software as well. And also, it is moving to cloud in a way, right? Because you need to make sure that for better elasticity for your workloads, you need to ensure that if it is in cloud, it's more budget. You can spend less money, and you will save a lot of cost over there. And the resource is vast and infinite there. And cloud burst is one of the very strong use case there. If you have a big workload, you can use cloud burst kind of a scenario. And coming to the decoupled computer storage, like we need to support different types of workloads now. As I mentioned, batch and services together, it should coexist in a way. So these are the new trends or the requirements as of today, which our resource orchestrators as of today need to solve. So let's see that where are we in terms of that. So we'll take each of the resource orchestrator and see that what are the strengths it offers as of today. And YARN is there definitely. So YARN is pretty much big data optimized It can run big data batch workloads much efficiently. It can give you the throughput that you need. If you want to run tens of containers, if you want to get maybe 1,000 or 2,000 containers per second to spin off, and if your batch workloads are low latency, it is there for you. It can actually withstand all the kind of pressure it needed in terms of the scheduling. Now, it definitely offers a better SLA, and it has a multi-tenancy, quota management, capacity planning. So all the things what is needed for a batch workload, it is there in the YARN perspective. So it's the strength of that. Now coming to the Kubernetes, it is optimized for running services. You can deploy, manage, and orchestrate your services well and better in Kubernetes, and a strong networking and volume support, and it's much cloud aware compared to the other one. So, and coming to the last, not but the least, like you have the public cloud as well there. So it is much cost efficient, and if you have more dollar, yes, you can get infinite resources there as well for your compute. So these are the strengths in terms of the multiple resource orchestrators that we are looking. Now, if I'm taking the recap, right, one of the earlier slides I mentioned, what are the new requirements, new trends actually is needed for today's resource orchestrators like Kubernetes or YARN to solve? These are the major ones. Like you need to make sure that your big data workloads need to be containerized. It is moving to cloud, and these are mixed workloads. So your orchestrator need to run both together. So now let's see that how each of the orchestrator is going to fare against this particular the new set of trends that we are getting. So in the Apache YARN world, so you know there are multiple resource schedulers, right? Schedulers, right? Like you have FIFO, you have fair scheduler, you have capacity scheduler. All are designed for certain use cases. And it actually runs very well on certain use cases there. You don't have a common one there again. And that is the first scenario. Second one is, if you look into this cloud, moving to cloud kind of scenario, right? You need to also run your microservices in YARN also. And that is possible today, definitely. There are features like native service. It is actually enabling YARN to do that. But it needs to be more efficient. And it needs definitely much better networking and volume support. And it also needs to be better, more elastic in nature, like auto-scaling and stuff like that. So these are the challenges actually. If I'm looking into YARN, what you need to solve for these new use cases. Now let's look at Kubernetes. In Kubernetes world, the biggest challenge for itself is running a big data workload. It's not that as easy as it looks, because it needs to run your microservice together and your batch workloads together. Both are different in nature. The schedulers of Kubernetes are not designed initially for you to run your batch workloads where you can spin up like thousands of containers in a second and shut it down after a few seconds. So it's not that way. So that is definitely a challenge for Kubernetes, and it does not have a better quota management. And in big data world, we all know that like the application is a first-class entity, but Kubernetes is like pods and containers. It does not have a notion of an application yet. So it has value actually in terms of you look into the big data world, because the application, you will get fairness across applications or FIFO order, a bunch of scheduling policies, right? Now, as I mentioned, these are the challenges that I have, and both need to somehow solve it. So let's see what is that single way to solve this problem, like that silver bullet, right? So let's see that what is there or not. But the way it looks like, there are none. There's no silver bullet at this point of time exists today to solve these issues. So how we can solve that, right? Then that means both resource orchestrators, let it be YARN or Kubernetes, they need to chase each other or like eat others' pie actually, and then spend more time in terms of catching up so that today's requirements can be met. And what is actually the problem there? It is too expensive in nature. It's because you need to invest a lot of cost to achieve that goal if I'm looking in perspective of each of the scheduler, each of the resource orchestrator. So let's look YARN first. You have services, and it can run on YARN today, but it is not as efficient as Kubernetes. And YARN has multiple schedulers. That means each scheduler is running in its own pace. So you have a new requirement coming in, you need to implement in at least 2 schedulers. So there's a lot of investment in terms of getting a new feature and getting it implemented. So that is the biggest challenge in YARN world. And in terms of Kubernetes, the natively can I run a big data job like MR or TAs there, right? That's not there today. And you have Spark there, but it is having a lot of gaps in terms of how it is running today. So again, you need to invest a lot of time there to get it to there. That the cost is very heavy, and there's a lot of feature parity as well, because if you want to get a high throughput or a low latency, it is not possible as of today. So in terms of adaptability as well, so there are actually the capabilities of YARN, and it's like, okay, you can run Docker for one application, and you don't need Docker for second one, etc. So a mixed way of doing is actually better for big data. But if you look in Kubernetes, it's all Dockerized, containerized. It is actually what is needed, but still, there is a gap there. So as I mentioned, it's a bunch of things which are actually cannot be solved simply. It needs a lot of time and investment, maybe years, to solve this issue. So the way if you look into it, YARN cannot replace Kubernetes, or Kubernetes cannot replace YARN in terms of scheduling perspective, because you're running big data jobs on Kubernetes or YARN, and you want to run service also on somewhere. So if you're looking into that scheduling perspective, it's not that easy to replace one another. So that's the reason why we were trying to see what we can do to improve, like if say in Kubernetes world or in YARN world, to reach there. So it's only an improvement, right, to see that where it can take us. So in that perspective, also the YARN is actually, YARN community is also doing a lot of things, like at this point of time to do this catch up, like trying to improve the cloud aware scenario. There's YARN 9548, you can see. It's actually very actively working on. So they're trying to make it more budget control or cost awareness kind of scheduling there, and CSA kind of persistent volume, networking improvements. So this is actually happening in the YARN world as of today. And in Kubernetes world also same thing. They're trying to make it more batch aware for their jobs, and they're trying to improve the Spark on Kubernetes. And in terms of CDP, yes, we are going to run few of our services in Kubernetes as well. Now, what are the motivation for me, like from our perspective? If you're looking into this, there are multiple schedulers which are actually powering YARN and Kubernetes. And these are for different use cases. So YARN has at least 2 to 3 schedulers. Now Kubernetes has 2 to 3 schedulers, everything for different scenarios. So the problem is the schedulers are fragmented, and it's not optimized, and it has very poor resource utilization if you want to run both clusters together, right? So what we are really trying to do is, like, we want to improve this scheduling world of both YARN and Kubernetes together, and hence we feel that there should be a unified resource scheduler and application management for both. So that is where actually we are going to. So I'll hand over to Veve here.
Thanks, Sunil, for giving the context why we are having this work and why we have this proposal. First it's about the name. We call it a YuniKorn, and initially Y is taken from YARN, and K was taken from Kubernetes, and the Uni was for unified, because we're trying to create something as unified scheduling experience. So the pronunciation is same as YuniKorn. I put it's not our logo here. It's just search from the internet. So I hope you like it. So some keywords here. So first, it's a common resource scheduler. It's not specifically for certain platform. Second, it's platform independent. It means it can run on YARN, on Kubernetes, or even other platforms. Third, it provides enhanced scheduling capabilities. That is basically based on all the experience we have on large-scale system about scheduling, fixing scheduling problems in past few years. So let's dig a deeper further what YuniKorn is. So YuniKorn is from our perspective, it will be a better scheduler for Kubernetes in Kubernetes world, and it will be supporting both service and batch workloads, and most important for big data workloads. And second, it is a unified scheduler as well as for YARN world, because in YARN we have multiple schedulers moving on. There's a lot of it's quite difficult to keep both of the schedulers moving forward. So instead, we put a unified scheduler, and we're going to continue to add more features in this unified scheduler for the YARN world. And third, it will be providing a unified resource scheduling experience across YARN and Kubernetes and beyond. That means we have a unified system to manage all the resources, no matter it was from YARN or Kubernetes. And as a design principle, we also want it to be suitable for both on-prem and the on-cloud use cases. But importantly, so it is not a system to let you run YARN application on Kubernetes without any modification or you want to run Kubernetes application on YARN without any modifications. That's not our goal. Next few slides will be more technical. So first, let's explore the feature set. When we talk about a good scheduler, we usually categorize four scheduling feature set. First one is the capacity planning. Capacity planning means when I get a cluster, I need to plan the resource for different users, groups, organizations, and we want them to be well managed. That will be having some limits or quota. This will give you a way to sharing resources between multiple tenants. Second is resource scheduling. This will involve like the resource fairness, preemption. This will ensure your application doesn't run be starving and or some malicious application using a lot of resource from your cluster. And also, very important thing is the high throughput. It's critical criteria for the batch system to support multi-tenant and placement constraints. That is the very essential feature to support different resources or different type of machines. Also, it will need application management, which means we need a central place to manage all the applications from different users, and we need a way to say what is going on in my application, what's the resource as it used. The last one is the resource monitoring. So this is also important to, that is basically give you a central place to manage all the resources on your cluster. So let's get a deeper more about each of the features. So capacity planning, it will have, this is like I just mentioned, this is for you to divide your cluster into different queues or resource pools in order to share resources between users and groups. So a few things important. First is the hierarchy of queues. This is the way we can actually map the queues to the real world structure or organization. So that would be the common use case for most of the users. And elastic capacity, that means we can set guaranteed and max capacity for each of the resource pool or queue. That means the resource usage can be elastic within this range for this for this queue for these users. That will be important. I'd say kind of important for you to find a balance between the utilization of the cluster and the SLA from the different applications. Third is resource quota. So resource quota is to let you set a resource cap for queues or for users. So limit amount of resource queue users can use, or limit number of applications they can submit. The last one is partition. This is usually we use it for isolation, right? We can partition the cluster to the different partitions, and all those workloads can be isolated, physically isolated. So this is the important things we think in the capacity planning. Next one is the resource scheduling. This will be pretty important for when your system have both services and batch workloads running. Services are low latency, and they are long running. Batch, they require high throughput, and most of tasks are short-lived. So when those applications come together, submitting into one system, how you can run them together without influence the other? So there are four important features. First is the resource fairness. That would be having multiple dimensions, including queue, user, application level fairness, and it will ensure each entity gets its own fair share. Second is the priority. This is basically how you can ensure your most important application can get the resource first. Most important user can happy. So preemption is the last option you have to get your most important application get a resource when something bad happens. Some of the resources being used be shared to other queues, for example. Placement constraints. So it's also important when you have co-located lot of applications, they have different needs on the, regarding in terms of affinity to nodes or other applications. When we have this feature set, we can have fine-grained control on how application being distributed to the cluster. So those are the very essential features we needed for the resource scheduling. Then is the resource monitoring. It's also important, especially important for Kubernetes, because we need a way to manage our resources in a central place. I get a screenshot here, but later I will go through a little demo that will give you more information about how we can actually plan the resource from a unified, from a centralized place, and how we can monitor the resource usage from different queues. Then is application management. So this is also important because this is how user can actually say what's going on with my application, how many resources it is using in each application, and how about all the history, those information will come from here. Then let's take a quick look about the architecture. You might be curious about why we call it a unified scheduler. So in this architecture picture is pretty simple. We have a master node, and we have a master service that is from the distributed system, and there's some bunch of other slave nodes. This system can be YARN, or it can be Kubernetes, or some other distributed systems. And in the master node, we'll be deploying YuniKorn core and a shim scheduler shim co-located with the master. So the scheduler shim is responsible to directly talking to the master with the language, the platform language. Like if we're talking to YARN, we're probably going to use the YARN Java API. If we're going to talk with Kubernetes, we're probably going to use the Go APIs. And the YuniKorn core is actually the most important, the central place where we have all the scheduling algorithms in this model. And each will talk with the scheduler shim through the scheduler interface. The scheduler interface is the common general interface we have created for the to isolate the actual scheduler with the underlist platform. So this is written in protobuf, and it will expose both gRPC and the Go API. So in this architecture, we can see the YuniKorn core only talks to the shim scheduler with the language that we specify in the scheduler interface. And the shim scheduler translates that into the language that the platform understands and sends that to the master and get the response back, of course. YuniKorn core and the shim scheduler works together for the scheduler, and the shim scheduler actually is a bridge to bridge the YuniKorn scheduler with the underneath platform. So in this architecture, we can easily, we created shim for YARN, then we can easily integrate with to run YuniKorn inside of the YARN cluster to take over the scheduling capability. Also, we can do the same thing for Kubernetes. We can create a shim for Kubernetes, then the scheduler will run seamlessly in the Kubernetes cluster. Then all the applications you previously running on YARN were running on Kubernetes, they will be still using the same way without any modification to run on these clusters. This is a simple table that we, because when we do this work, we have some investigation and research on other existing schedulers. We did some comparison here. This is from the perspective we think what are the most important things for a scheduler, including resource sharing, resource fairness, preemption, throughput, and gun scheduling. So those are the main features we want to compare. So each of them we dig into some of detailed features, and as you can see for YuniKorn, we are having most of the features ready. Some of them in working progress, and there's the first throughput. We don't have the data right now, but we're going to test it shortly. And we have some other planned features here. Then we can take a look quick demo. Apologize, this is recorded demo, and let's go through that. So first, this is Kubernetes cluster. I created the 5 nodes. All the nodes are from AWS, and we can go inside to take a look at each node. So each node we have probably 180 gigabytes memory and 48 CPUs. We're going to use this cluster to deploy YuniKorn as a scheduler to then some application to YuniKorn. First, to deploy the scheduler, we need to proper configure the scheduler. This is the configuration we used for YuniKorn. It is in YAML file format, and most important part is the queues, right? This is how you can configure multiple queues in for the scheduler. In this example, we have 3 queues. Under the root, we have advertisement, we have search, we have sandbox. And each of the queue, we can define the guaranteed resource and the max resource. And each of the resource you can have memory, you can have vCore, you have other whatever resource tabs you have in your system. And the guaranteed and max give you an elastic range for this queue can use. For example, for advertisement queue, we can use 500 gigabytes memory and at the most 800 gigabytes memory. And also, there are some other configurations here. It should be. Okay. That's the megabytes. And so you can add placement rules. That is basically how we can automatically map our applications to our queues. And also you can create user limits. You can define how many resources at most you want a user to use, how many most applications you want the user to submit. You allow user to submit. So there are coming more configuration, but all in search format. And this file will be created in a config map mounted to the pod that we're going to launch. So that will be loaded by the YuniKorn scheduler. Then we can take a look. We can create a config map on Kubernetes. Then let's go to the Kubernetes to take a look at the config map we just created. Here's the config map we just created. And the YuniKorn, we're going to mount the config map to the pod and load the configuration. Also, then let's deploy the scheduler. So this is the deployment YAML file for YuniKorn. It's very simple. It runs 1 pod, 2 containers. 1 container is for the scheduler core, which actually includes both YuniKorn core and the shim. The other one is the scheduler web, which is the user interface we have built. So, and you can see the volumes. It specified the config map here. That's how it can read the configuration. This is the volumes, and we're using the config map to mount here. Then we are going to use kube control to deploy this pod, just like other deployments. This is how you created a deployment. And then we can take a look at how if it is running now. Okay, in the deployment, we can see we have the pod is running. And go inside of a pod, we can see there are 2 containers. Just I earlier showed, so there are two containers. One is for core, one is for web. They're loading the image from a version, then yeah. So once the scheduler is running, then we can we can go ahead to submit some jobs, right? So first, this is do the port forwarding. So we can take a look at the UI. This is the YuniKorn UI. As you can see, we have a cluster connected. It is Kubernetes, 5 nodes. And this is a summary page. In the queue page, you will see the queue we just configured in the configuration file. In the root queue is all the resources you have, right? And you can click each box for the queue to view the details about the queue, including the min and max capacity we have configured, and use the capacity and in the absolute values and the percentage. Then we can expand and go into different levels of the queue in this page. Those are the queues we just created from the file. So each of the queue, you can check the details in the right side. Right now, because we didn't submit anything, so application page is empty, and the application status is also empty. But then let's try to submit an application. So we'll try to submit some. This is a very simple batch job using the job API from Kubernetes, and it will simply launch 50 ports in a job, and these 50 ports simply sleep 300 seconds for each of them. And you can see in the labels, we have specified application ID here. Also the queue where you want to submit. YuniKorn basically will pick up the application ID and the queue information from here to determine where you want to run your job application. Then simply we can use Control T to create a job. This is we're going to submit the job to sandbox queue. It's, once it's submitted, we can, in the Kubernetes UI, you can see the ports are starting and they are coming. Remember, we have submitted 50 ports. They will be running in a few seconds. And then you can, in the YuniKorn UI, you can see to track the resource. There's a little blue bar there that indicates how many resources you have used in this queue. And also you can see the sandbox queue. Because we submitted 50 ports, each of them require 2 GB memory, so it used almost all the resources in this queue, and the color turns red. Then in the application page, we can see the application is running here, and we can also click and see how many tasks is running under this application. So there's no such view in Kubernetes. You can keep tracking of this information. As you can see, we can see all the running ports here. It will give you all the information about the application, like the resources used and when it is launched. And then we can submit another job. This is how usually user use, right? You have multiple queues configured, and you have a lot of more jobs to be running. This one is simple, another simple job. It will be submitted to another queue. Let's see how it happens when we submit to the other queue. The first job should be running, and the second one is coming up. Once it is started, we can also see how resources are used in our UI. The sandbox are used up, and the advertisement queue also have some of the resources being used by this application. Those are very simple job API provided by Kubernetes. So we can also submit other whatever you want, like deployment or replica side, as long as you have those labels I just showed you set. They'll be scheduled by YuniKorn scheduler instead of the default one. Then Then we'll submit a Spark job. This is script we use to submit Spark job. There will be submitted Kubernetes cluster, and deploy mode is cluster. It's a simple Spark Pi job, 5 executor instances, and it will leverage the pod template. Basically, we can set some of the configuration for the pod in this pod template. We can actually take a look at that pod template. The pod template, we will give the Spark app ID here, and the queues we are going to submit. This time we're going to submit to advertisement. Okay. If you run Spark on Kubernetes, you don't really have a view to track the Spark application. But YuniKorn UI provides give you the application where you have the Spark application here. You can see the port it's being using. It's finished, so it's very simple job. Then let's the ports are being running and here. Then let's take a look at the queues usage. Okay. Because the Spark job is done, so it released the usage. But we can see the sandbox we have. We don't really have any resource anymore. Then let's submit another Spark job to the sandbox queue. Let's see what happens. This is just a similar script, just to run the Spark job on sandbox queue. Let's see what happens. As you can see, the port will be pending there. The port will be Spark driver port will be pending. The pod is pending, and the job cannot be running because in the sandbox queue, we don't have any resource for new application. It's already reached the max capacity of the queue, so it will not be scheduled. Yeah, I think that's the demo. Then do you want to talk about next?
Yeah. So this is a demo that same architecture we have just shown. I'm just sorry. Yeah, just to give you a perspective that Grafana promotes all the integration to all the world, and it's been an end-to-end one. And just for the today's perspective, like we just use Kubernetes actually as the orchestrator to demonstrate. It's a short demo, so we didn't have time for the YARN one anyway. So just quickly moving over, the takeaway that we want to definitely give out, right? You have scenario one, and before and after, 2 columns, right? So you have a Kubernetes cluster on cloud on-prem. You are using existing Kubernetes schedulers. The YuniKorn can replace there. You have both Kubernetes and YARN goes together. And in YARN, you have 2 different schedulers as well. But if you go on the other side, you can see Kubernetes and YARN can use one single scheduler to effectively utilize your complete resources. And YARN cluster itself, you don't need to have multiple schedulers. You can have one YuniKorn scheduler. So this is a takeaway that we definitely want to put it across and how we want to envision and take it forward. I think the time is also running away, so the critical one. Yeah, we are going to open source it soon, and stay tuned. It will be very soon. You'll be able to get a pick of that. Yeah.
This is part of the HTTP or CDP?
It's an open source project. Yeah, in the Hadoop one. So in terms of product, yes, we are actually discussing it out when it will come there. A quick acknowledgement to the folks who are done. Many folks from the YARN community helped into this one. And yeah, so that's pretty much it. And we have some time for, not much time, but yeah, we'll definitely try to take questions. Yeah. Yeah.
Thanks.
Yeah.
So this is very interesting, and I'm just curious, like being sort of like a Hadoop conference, like I think we're all pretty much comfortable in using YARN today. What's the driver for doing this on Kubernetes for us and for you? Is it sort of like a hedge in case Kubernetes becomes something gets more steam? And for us, is it because maybe we have Kubernetes in-house to manage things like Docker, and there may be a shift?
It's not that way because, as I mentioned, right, in the Hadoop world and YARN world, you have different schedulers as of today. And each of the schedulers are actually need to become more cloud aware. It need to be like, okay, schedule for bin packing and all these kind of new requirements which are needed for better elasticity and to save cost. So all these things are actually, that is being driven in the YARN community as of today. So that is actively happening. Now with the YuniKorn, addition to this thing, with the YuniKorn coming into picture, so we'll have one single scheduler where we can invest the core effort from our end so that YARN will become even more very powerful in that perspective. Yes, and if you're doing a new scheduler, so why not we do it actually generic one, so that even Kubernetes does not have that power as well. So it is actually making sure that the focus of the YARN is very much there and make it even more powerful for the new use cases what we are getting today. So that's the exact message that we are actually trying to get.
And how has the Kubernetes community responded to?
As I mentioned, it's a first talk we are giving.
Yeah.
The first time we are actually openly mentioning about something like this is there. So it's in the very initial stages. So this is what we are offering. It will get open source, and the feedback from there will be different. That is actually it to comment on that line.
Okay, thanks.
Yeah. Cool. Yeah. Thank you all for attending. Thanks.